10.2 is taking a sequence and finding the sum of it, right? So sequences are lists of numbers, whereas series are the sum of that list of numbers. And the one that's written here using Taylor series, sign 1 can be approximated and proven to be equivalent to the infinite series of 1 minus 3 factorial plus 1 over 5 factorial, etc. So convergence of an infinite series summation n equaling k to infinity of a sub n converges to the sum s if its partial sums converge to s, right? Or in other words, if the limit as n approaches infinity of s sub n is equal to s. In this case, we write s equals the summation from k to infinity of a sub n. If the limit does not exist, we say that the infinite series diverges. And if the limit is infinite, we say that the infinite series diverges to infinity. So we're going to investigate this one telescoping series numerically. And it's important to note that one of these methods that we should be adding to our list of different ways to analyze these, it is using partial fraction decomposition, right here. So the first thing, we're going to take a look at this series and see how we can investigate it in both ways, right, using the partial fractions or not. So what I mean by that, s of 1, right, the sum of the first term, can be found by doing the 1 over 1 minus 1 over 2, which is equal to a half. S of 2, which would be equal to a half plus the second term, which is most simply found by doing 1 over 2 times 3, or we can use the partial fractions here, and we would say, well, S1 was 1 over 1 minus 1 over 2, plus S2 would be 1 over 2 minus 1 over 3. And we can see that those internal fractions cancel, and this reduces to 1 minus 1 over 3. If we continue this just a couple times, enough to establish the pattern, S of 3 could be found by simply doing 1 half plus 1/6 plus 1/12, or, again, 1 over 1 minus 1 over 2, plus 1 over 2 minus 1 over 3, plus 1 over 3 minus 1 over 4. And again, those internal fractions cancel out, and we're left with 1 minus 1 over 4. So in general, S sub n is going to equal 1 minus 1 over n plus 1. And if we take the limit of that, it's going to equal 1, right? Because this term would zero out. Example 2 in section 10.2 has us just looking at the differences between sequence versus series. And we want to discuss the difference between a sub n and the summation of a sub n from 1 to infinity, where a sub n equals 1 over n times n plus 1. So main thing, definition-wise, a sequence is a list of numbers. Right? So if we were to investigate this, in this case, it would be 1 over 1 times 2, comma, 1 over 2 times 3, comma, 1 over 3 times 4, etc. Right? This sequence, we can see, converges to 0. Right? The denominator is growing without bound. The numerator is not growing. So the sequence converges to 0. Eventually, the nth term would be almost 0. And then we could say that the limit as n approaches infinity of a sub n equals 0. But on the other hand, the infinite series, the sum of this sequence, in other words, So infinite series, or sum of the sequence, right, in this case is not 0. Another way to talk about the sum of an infinite series, because infinite implies that obviously it goes on forever, we would look at the partial sums, the limit of the partial sums. And in this particular case, the sum is not 0. Keep recording. Okay. Summation n equals 1 to infinity of a sub n would then equal, right, the 1/2 plus the 1/6 plus the 1/12, etc. This converges to 1. And this is something that was a series that we had investigated before. And we'll continue to look at things like this. But the main focus here, sequence versus series. Sequence is just that list of numbers. Series is the sum of the sequence. So our next example, actually the next page just brings up some theorems that are definitely important. Theorem number 1 up there, that's one of those where we use it. We don't always acknowledge that we're using it, but it's the linearity of summations, of sums, or of infinite series. So we could either add them separately or add them together. So it works in both directions. Sometimes it benefits us to go in both directions. Subtraction, same idea, as well as coefficients or constants. You can pull them out in front and multiply your final answer by that constant. Number 3 is not one that's going to be used directly, but it is part of the kind of proof and arriving at theorem 2, so I threw it in there. If you want to take a look at everything leading up to it, it's certainly in the textbook. But 4 and 5 we will use. So sum of a geometric series. C is not 0, of course, otherwise the series would be 0. And if the absolute value of r is less than 1, then they are going to converge. If the summation begins at 0, goes to infinity, we simply use c, the constant, divide by 1 minus r. And that would be the summation or the partial sum for the infinite series, the geometric one. If your summation is not beginning at 0, it's beginning at some other positive value m and going on to infinity, then we just need to account for that in our numerator and do c times r to the m power wherever you begin at, divide by 1 minus r. C is that initial value. Go for it.
Ms. Hartman, can you explain the same part again? How, if r is greater than 1, it converges to infinity, right? You can't calculate the
Yep. That's the final part here, Mullen. Absolutely. If r is greater than 1, it'll grow without bound. It diverges.
Got it.
Yep. So these two formulas are used if that ratio is less than 1. If the absolute value of the ratio is less than 1. Okay?
Got it.
Cool.
Got it.
And we're going to do a couple of examples on this next page.
Ms. Rodriguez?
Yes, Simon.
I was wondering, will it specify when you're allowed to use a calculator or not?
This portion is calc active from what I've observed so far. So I suppose that the calculator can help you toy with numbers and things such as that, and maybe there's more capabilities that I'm unaware of, but ultimately you need to be able to employ these different tests that we're going to go through in order to really conclude, because oftentimes it's just simple of like, does it converge or diverge? It's not looking for like some numerical answer all of the time. But from what I'm observing so far, much of the multiple choice for this has been calc active because it's not that helpful. All right, so examples 3 and 4 on these geometric series. So observation on the first one here, it's the summation from 0 to infinity of 5 to the negative n power. So you don't have to start listing out the sequence. I like to, sometimes at least, just to get a feel for, well, what are these values? Then maybe it's more clear to say what's the r, what's the c, etc. So I'm observing that it begins at 0, so I can use the c divided by 1 minus r. And my first term, beginning at 0, would be 5 to the 0 power, or 1. My second term would be 5 to the negative 1 power, or 1/5. 5 to the negative second power, or 1 over 25, etc. So I mapped it out in this one just to say, okay, now I can see to go from one term to the next, yeah, I'm multiplying by a fifth. And then I'm going to continue to do that same thing as I go to each subsequent term. So then there's my common ratio. My constant, it's just a 1. It began with a 1. I'm not multiplying my numerators by anything at all. So then this answer is as simple as saying it's just 1 divided by 1 minus 1/5, or you can write it as 5 to the negative 1. And here we would get 5/4. So if we continue to list out this sequence to infinity, right, the sum of that would end up being 5/4. The second one, example 4 here, begins at 3, right? So that means that we're going to use the second from the theorem. We're going to account for the fact that it's not starting at 0, so we need to use the c r to the m over 1 minus r. And then it's the same thing. They already listed it out for us, which was nice. So we can see that that ratio is a negative 3/4. We can see that that c is a 7. And then the m is a 3. So when we go to our formula, we have 7 times negative 3/4 cubed divided by 1 minus, in parentheses, negative 3/4. So then we would have 7 times negative 27/64 over 7/4. Lots of things end up canceling for us. The 7s cancel. That 4 can go into the 64 16 times. So you end with negative 27/16. Okay? So I observed, right, it is geometric. R is less than, absolute value of R is less than 1. N was not 0 here. And then I just used the formula. Okay? All right, so example 5 begins a little differently, but we're eventually going to use the same exact thing. This is also going to help us, the linearity of summations is helpful here. So I can first break this fraction up and say, well, this is equivalent to n equals 0, infinity, of, I'll write it as 1 for a second, 2 over 5 to the n plus, oops, I said I was going to write it as 1, so let me actually do that, plus 3 to the n over 5 to the n. And then from there, I can start breaking things apart. I could pull that 2 out. I can write it as 2 summations, one of which is 1 over 5 to the n. The other one, I want to pull the n power out so that I can see my ratio. My ratio is 3/5 to the n. Right, so now I have 2 geometric series happening. I have that constant of 2 out in front, so I could just leave it there. Both of them I'm observing. Whether I pull this n out here or not, it doesn't matter, right? It's 1/5 to the n, so I could pull it out and have parentheses around it like my second one is. But either way, my common ratios are both less than 1, so I can use, and they're both starting at 0, I can just use the c over 1 minus r for both of them. So I have a 2 times 1 over 1 minus a fifth plus 1 over 1 minus 3/5. And then just through simplifying them, I would get to my answer. So 2 over 4/5 plus 1 over 2/5 here. So then I end up having 10/4 plus 5/2, which is 5. Okay, so all of those common ratios were smaller than 1, so they all converged to values. All right, this next test, Theorem 3, is called divergence test. This is one of those things, it has to do exactly as it says. And what I mean by that. So the divergence test says if the nth term a sub n does not converge to 0, then the series from 1 to infinity a sub n diverges. Right? If a list of numbers doesn't zero out, then it diverges. The series does. But if it does zero out, that is not enough to prove convergence. So we can't assume the opposite here. It only proves the divergence statement. All right, so use caution there. So it's only a little helpful, really. So I'm going to write that. If a sub n goes to 0, this does not. I always spelled guarantee wrong. G-U-A. Unt, like U-N-T or A-N-T? A-N-T. E-E. Guarantee convergence. Prove the divergence of S, right, the sum, from 1 to infinity of n over 4n plus 1. So the first thing, right, we're dealing with divergence test here, so we need to really take a look at the a sub n. What does it do? So I just want to, first of all, define a sub n, obviously, as the n over 4n plus 1. And if I take the limit of that, so the limit of a sub n as n approaches infinity, or the limit of, as n approaches infinity of n over 4n plus 1. Well, we can take a look at that, right? The degrees are the same. It's growing at the same rate. So we just take it's 1/4. 1/4 does not equal 0. Therefore, we've just proven divergence. S diverges. So many of these problems, especially when they're multiple choice, they're quick, right? We have to have all these tools ready to go. Determine the convergence or divergence of this S. So from 1 to infinity, we have -1 raised to the n minus 1 power times n over n plus 1. And they've listed it out for us: 1/2, -2/3, +3/4, -4/5, etc. Okay, so right, we see our a sub n, we need to take the limit of that. So this portion, right, the n over the n plus 1, no problem. That's 1. This problem, and this is certainly shorthand, but it's okay to use shorthand here. This one goes from negative to positive, right? It's going to alternate. So overall, the limit here is 1 or -1. It's not the same, therefore it does not exist. And all that I care about, like that's why I don't have to keep going further, it's not 0. Definitely 100% not 0, therefore diverges. So that's why we can use shorthand. It's not really, I'm not looking at exactly what this is, one-side limits, etc. We're not in chapter 2 right now. I just needed to show that it wasn't 0. Okay. This sequence, the sequence itself tends to 0, right? So a sub n zeroes out, but the series diverges. So we're going to prove that. We're going to prove divergence, even though a sub n goes to 0 at infinity. So it's defined as summation from 1 to infinity, 1 over square root of n, which would be 1 over root 1 plus 1 over root 2, etc. So if we take the limit as n approaches infinity of a sub n, 1 over root n, right, that's 0. Even though root n is, the square root of infinity gets, it's a 1/2 power, it's not a massive power, it still will go to 0, right? The denominator is still growing faster than the numerator. This just simply means that it might converge. Right? We have not proven convergence because it's equal to 0. So we need to investigate. So I'm going to take a look at this S sub n. What does this sum look like, right? It looks like this. 1 over root 1 plus 1 over root 2 plus 1 over root 3 plus dot, 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 plus 1 over root n. So these individual terms are what? Getting larger or smaller?
They're getting smaller.
They're getting smaller, right? So therefore, we could make this statement that however far we go, any of these, right, even if we did only the first one, this chunk is larger than 1 over root n, right? Okay. Okay. So then this S sub n collectively is greater than or equal to, if we just kept on adding an n amount of 1 over root n's. Right? This is the true sequence and as a sum series. But I'm just trying to show that this is larger than this. Right? I know that this is not the actual series, but all we need to prove that is one is bigger than the other for right now. And what we're arriving at is, we just change color so it stands out more. This right here is equal to n times 1 over root n, or root n. So because these are larger, then this whole thing is larger than what I'm making up over here. N amount of these 1 over root n. So if we just kept on repeating at the end forever and ever and ever, that's bigger than that, but that's equal to this, root n. And root n increases without bound. So S of n in conclusion is greater than or equal to root n, but root n increases without bound. Which means the S of n must also increase without bound, and therefore diverges.
But I am a little bit confused.
Sure thing.
Yeah.
So there's going to be a lot of times where you can't directly prove something, okay? So you have to make up something that's comparable, similar, comparable, but that you can concretely come up with an inequality for. Because magnitude of these series is significant. If one is larger than the other, that's going to allow us to prove certain things. And we're going to actually come across a few tests in a minute that go along these lines. But all I'm trying to show right now is that even though this thing at a sub n, the nth term, gets closer and closer to 0, if I add them all up, I'm not actually going to go to 0. I'm still going to go someplace without bound. So I needed to show that. So I manipulated the fact that this chunk is definitely bigger than this by itself. And then therefore if I had, so now over here I'm not really working with the exact series, I'm manipulating and I'm picking something a little bit different, but something different enough that I can prove my S sub n is actually larger than it. So because this is bigger than this, if I have an n amount of these final terms, and I simplify it, n times 1 over root n's, rationalized, it's root n. Root n by itself, still sticking with my inequality, is smaller than my S sub n because of what we've set up here. And therefore, if root n, as we approach infinity, is unbounded, then S of n, as we approach infinity, must also be unbounded.
Why do you multiply by n on the?
Because I'm saying I have an n amount of them.
Okay.
I go on forever. Or n times.
Like, what if there is no square root above the n? Is it going to be different?
Yeah, there's, again, this is the type of stuff that the challenge becomes. You have to be creative oftentimes in how you compare things. So this isn't necessarily the exact way you're going to do the next problem, but the idea behind it of either finding something larger or smaller to base your proof off of.
Yeah, but I mean, it is like getting smaller and smaller and smaller and smaller, and the new term is becoming more and more insignificant.
Correct. The nth term, that's true. But the total series added up does not zero out, is what they're saying.
Okay. Okay. I'll try to like work this out in my head, and then
Even sometimes graphing it, right? A lot of times, and again, we're going to get there in a few more tests, but graphing it, there's an integral test. The idea of the integral, the summation, the area under the curve, if you think of it graphically, you can see, oh, there's space. Even though it does approach, there's still a lot of space. It's not going to zero. There's still some area. So similar here, I understand, when you're saying it's getting smaller and smaller and smaller, but it kind of like, for things to zero out, right, like the magnitude here has to be opposite the magnitude here, right? Like this needs to cancel with this, and this, and this, and this, and this, etc. That's not happening here, which is why it's not zeroing out. That's another way to think about it.
That makes sense now.
Right? There has to be a balance between things canceling one another out to get to the concept of zero.
That makes sense.
Okay.
Thank you.
You're welcome. Woohoo! That's 10.2. All right, I'm going to